The tangent lines to a circle theorem says that a line is tangent to a circle if and only if it is perpendicular to the radius at the point of tangency. Okay? A line is tangent to a circle if and only if it is perpendicular, which I think we know this, but just to make sure, forms a right angle, 90 degrees, to the radius at the point of tangency, where it touches. Okay, now, these if and only if statements. Okay, an if and only if statement means you can go both ways with the statement. So, what I mean by that is if I know a line is tangent to a circle, then I know it forms a right angle, or it's perpendicular. Okay, vice versa. If a line forms a right angle or is perpendicular to the circle, then I can call it a tangent line. Okay, I can go both ways with that relationship. If I know one of the things, then the other one's always true, and vice versa. Okay, that's what an if and only if statement means. So let's use that logic here to answer these two questions. We're going to refer to the figure shown to the right. It says if line L is tangent to circle O at point A. I stop right there. What do I know? If L is tangent to circle O at point A, what can I draw on my picture? A right angle here at A. I can draw a right angle there at A. Okay, let's keep going. It says the radius of the circle is 4 inches. So where do I put that on my picture? OA. OA is the radius. So I can put 4 right there. And AB equals 3 inches. What is the length of BO? Well, how can we figure that out? Pythagorean theorem. We got a right triangle right there, so we use the Pythagorean theorem. So 3 squared plus 4 squared equals our hypotenuse squared. So that's 9 plus 16, which is 25. So that means that our hypotenuse, BO, equals 5 inches. Okay, it equals 5 inches. Now, here's something you need to know. 3, 4, 5 is a special case of a right triangle. Okay, if you didn't learn that in math too, 3, 4, 5, if you were told, like I knew the answer was 5 before I didn't even have to do the Pythagorean theorem. Okay, because I know 3, 4, 5 triangle. If the two legs are 3 and 4, then the hypotenuse is 5. If I'm told that the hypotenuse is 5 and one of my legs is 4, then I automatically know the other leg is 3. I don't have to use the Pythagorean theorem. It's just one that I need to memorize. Okay, y'all need to memorize that. 3, 4, 5. It'll save you some time on the ACT because almost every sample ACT I've seen has had a question with a 3, 4, 5 triangle line. You can save yourself a lot of time by not having to actually compute it. Okay? So part B, I gave you another copy of the circle there, so that because we're resetting. Okay? A, we're done with this stuff from A. We don't that doesn't apply anymore. We're using the same diagram, but we're using different measures. It says if AB is 5 centimeters and AO is 12 centimeters and BO equals 13 centimeters, why is it correct to conclude that line L must be tangent to the circle at point A? Any ideas of what we should do to show that it is actually tangent? Huh? See if it's a right angle, okay? How do we test if it's a right angle if we have the measures of the legs? If that's a right angle right there, what should these 3 measurements satisfy?
Oh, you gotta the 2 smaller ones add up to the exact. Yeah, they're bigger.
Yes, they have to be bigger. That's just That's the qualification to be a triangle, okay? But to be a right triangle, the Pythagorean theorem. It has to satisfy the Pythagorean theorem. So let's check and see, does 5 squared plus 12 squared, does that equal 13 squared? I put a question mark over my equal sign because I don't know for sure. Clay says that it does. Do we trust Clay?
Yes.
Yes, we should trust Clay. It is 169 on the left side. It is 169 on the right side. So it does satisfy the Pythagorean theorem. So I can't spell satisfies this morning. Satisfies. There we go. It satisfies the Pythagorean theorem. Therefore, these 3 little dots in a triangle mean therefore there's a right angle. At point A. Okay, so it satisfies the Pythagorean theorem. So if there's a right angle, therefore it's a tangent line. By the way, 5, 12, 13 is another special triangle. Okay, 3, 4, 5, 5, 12, 13. Oh, here's the thing that I forgot about special triangles. Multiples of that work as well. So if we've got 3, 4, 5, 6, 8, 10 is also a special triangle. Okay, 6, 8, 10 because all of them will multiply by 2. Or let's see here, 12, 16, 20. Okay, 12, 16, 20 is a special right triangle. It's multiples of that. 10, 24, 26. Okay, if the hypotenuse is 26 and one of the legs is 10, then I know the other leg is 24. Okay, any multiple of 3, 4, 5 or multiple of 5, 12, 13 is a special triangle. All right, I added a question to this. What is the distance from point B to the circle? Anybody know? What is the distance from point B to the circle? What's that distance right here?
3.
Where did 3 come from? You just guessing?
Well. Is it right?
No, it's not right.
It's 2.
It's 1. It's 1. Why is it 1, Sierra?
The radius is 12.
The radius is 12. We can put a radius wherever we need it. Any point that goes from the center to the circle has the same length. So this is 12. The whole thing's 13. So this little piece right here is 1 centimeter. Okay? 1 centimeter. All right? So everything we know about circles up to this point still applies. All right? Y'all know this about radii. You just kind of forget to apply it. But you can put a radius wherever you need it, from the center to the side of the circle, not triangle. Triangles don't have radii. They have centers, they just don't have radii. Speaking of centers of triangle, what creates the incenter? What creates the incenter of a triangle? Huh? The angle bisectors. Incenter starts with a vowel. Angle bisectors starts with a vowel. How about the centroid?
Perpendicular bisector. No, the radius.
The medians. The radius. I just said triangles don't have radii. Okay, the centroid is the medians. Remember, the short one goes with the short name. Okay, and that leaves us with which one? What's the last one?
Perpendicular bisector.
Okay, perpendicular bisectors, but what's the last center? What's it called? It's got the weird name. Circumcenter. Okay, circumcenter is perpendicular bisectors. All right. Not circumcision. Let's not go there. All right, here we go. Let's keep going. Now suppose you are given that PA and PB are tangent to a circle centered at O. So if they are tangent, what do we need to do? we need to come in here and put the right angles where they are tangent to the circle. It says to help prove that PA is congruent to PB, auxiliary line segments OA, OB, and OP are drawn in the figure. What that means is they're extra there to help us. Okay? It says, how could you use congruent triangles to prove that segment PA is congruent to segment PB? All right, so, yes.
Because if those two angles are the same, that means the side lengths are going to have to be the same. So then you have, an isosceles triangle, which means that angle has to be the same.
I think Hannah got it right.
Okay. That is one way. It's not congruent triangles, but okay, you kind of can't use that because the whole thing is not a triangle. Because it has four sides. It looks almost like it goes straight across, but it doesn't go quite straight across. All right, so tell me, what do we know has the same side length? What do we know right now that have the same length? The middle pieces, right? OA and OB. Those are radii, so they have the same length. You were talking about that piece right through the middle. I'm sorry. That middle piece in the middle, remember that reflexive thing? When they share the side, obviously they have the same measurement. Okay, so somebody tell me, do y'all remember any of the congruent triangle theorems? No.
Yes.
Okay, side to angle is not one.
Angle, side, side.
Angle.
No.
Can't do that one.
Side, angle, side.
Side, angle, side, yes. Angle, side, angle. Side, side, side. Angle is similarity. Okay, that's similarity. Okay. Was there another one that just had two?
Side, angle. Angle, side.
It only had two. Okay.
She said,
Did y'all learn hypotenuse leg?
yeah.
Yeah, hypotenuse leg. Is that what we have right here? Yes, we have the hypotenuse and the leg. So those are congruent triangles. So hypotenuse leg. Okay, but here's the important part. Okay, I wanted to review that. Number one, the important part is the conclusion. Segment PA is congruent to segment PB. So here's the other thing about tangent lines we need to know. Not only do they form a right angle with the circle, then if they come from the same exterior point, okay, exterior point, exterior means outside, right? Exterior paint goes on the outside of your house. Exterior point, so in this case, that's point P. So the theorem says that segments drawn tangent to a circle from an exterior point are congruent. So if we know that those two segments are tangent, they form right angles with the circle, they come from the same exterior point, then they have the same measure. They have the same measure. Okay, always. Same exterior point, tangent to the circle, they are congruent to one another. Always. All right, so those are the two things that we need to know about tangent lines to be able to apply them. The other thing, let's look at this picture just a little bit more carefully. Since these are congruent triangles right here, then this angle, let me use a different color. This angle and this angle are congruent. That line right there in the middle bisects that angle at P. They have the same measure right there. Okay, we're going to need that here in a minute. And obviously that would mean that these angles right here are congruent to each other. Okay, because they are congruent triangles. All right, we may need to use that here in a little bit. Okay, so let's look at this problem right here. Check your understanding. It says, we're going to talk about a satellite that's orbiting the Earth. This picture right here is supposed to represent us looking directly above the Earth, directly down at the North Pole, and the equator would be the furthest point out that we see around the edge of the Earth is the equator right there. Okay, so let's read the rest of the problem. Suppose the satellite is located in space at point S. In its view of Earth, in the plane of the equator. So it's looking straight at the equator. Okay, the angle between the lines of sight at S is 50 degrees. So this angle between the lines of sight at S is 50 degrees. 50 degrees goes right there. They also tell us that the radius of the Earth is 3,963 miles. So from the middle point there to the side, that is 3,963 miles. We can put it there. We can also put it right here. These are tangent lines, so let's fill in our right angles. All right, so that's all we know right now. It says, what is the distance from S to the horizon along the equator? That is the length of a tangent from S to Earth's surface along the equator. So we are looking for this measurement right here. Now, can we really do anything with it the way that it is? No. Pretty much all that we know is that the other side has the same length, but we still don't know what it is. Is there something else that we can put in here to help us out a little bit? A line in the middle. Okay, how does that help us out? Creates two triangles, right? It's just like the last picture we were looking at. It makes us two triangles. So what would be the angle right here in the triangle? 25. We just talked about that. It cuts it in half. Okay? So, what can we do now?
We can find another angle.
Okay, we can find another angle if we want to. Does that really help us out, though? No, not
We
really.
can do
Okay.
side angle.
Okay, but how does that help us solve for the side?
We do.
How can we solve for the side? Think math 2. Think math 2. Trick. Okay, y'all didn't learn much in math 2. I do know this, but I do know that y'all learned SOHCAHTOA, right?
Oh, yeah.
Oh, yeah, that's the one thing that everybody always remembers from math 2. So, what was it? SOHCAHTOA, or what else did y'all learn? Some old hippie caught another hippie tripping on acid. Oh, yeah. All right, so we need to identify which sides of the triangle we've got and which side we're solving for. So, which side do we have?
We have a leg.
Is there a leg in any of that trig right there?
We have an angle, and we have.
Yes, we have an angle. Which side? Which side do we have?
The bottom one, tangent.
Okay, I know what the number is. Okay, I'm looking for one of 3 words. Opposite, adjacent, or hypotenuse.
Adjacent. Opposite.
Opposite, okay? Opposite. All right, so everybody's at a different place with this, so I just want to give you my hints for figuring out which side's which. Okay, number 1, I think most people are okay with the hypotenuse, but in case you're not, use the right angle as a little arrow. It points to the hypotenuse, okay? So we definitely don't have the hypotenuse. We do not know the hypotenuse right now, okay? The other thing that I do is right here, the angle that I have, I like to extend that little angle symbol there Okay, the other side that it touches, touches adjacent are beside each other. Okay, it touches, so the adjacent is x, so then that leaves the 3,963 for the opposite. Okay, so we have the opposite, we want to know the adjacent, so which trig function do we use? Tangent. Okay, tangent. So let's set it up. Tangent of the angle 25 degrees is equal to the opposite side, 3,963, over the adjacent side, x. So how do we solve for x? Okay, how do we solve for x?
He gave you 3-0.
We times by x.
Okay, we multiply by x, and then we're going to end up dividing by tangent. Guess what happens? Pretty much those two things just switch places. Okay, they just switch places. Because you multiply, and then you turn right around and you divide. So let's just combine those two steps and switch places. You multiply by x, and then you divide by the tangent of 25. Okay, now it's just calculator. But what do we have to remember? Put it in degree mode, because we're plugging degrees in. You got to make sure you're in degree mode. Y'all love to reset your calculators. Every time you reset it, it goes back to radian mode. Mode. Degree mode. So you go to mode. All right, so we are approximately 8,498.7 miles from the horizon along the equator. Okay, that's part A. Let's look at part B. How high is the satellite S above Earth's surface? That is the length of a segment S to the closest point on Earth's surface along the equator. Now, I don't want you to just blurt out. I want you to think for a second. Then we're going to put it all together. Okay, we're trying to find the distance from S to the closest point on the Earth. Ideas.
Take the number we just got and minus it by the radius. Subtract.
Okay. Is this segment the same length as that segment?
No.
Oh wait. Oh, we got that side. We got.
I was gonna say, can we just draw a tangent line, just that one point, make it smaller? Can you use on that green theorem and then subtract the radius?
Okay. We can use Pythagorean theorem because now we have two legs of our triangle. That's going to give us our hypotenuse. But we don't need the whole hypotenuse, right? Noah said then we subtract the radius because we're looking for this distance outside. We know the distance inside, so if we find the whole thing, subtract what's inside, we'll get the point or the distance outside. Okay, so that's our leg. Square it. Plus our other leg squared, really big number. Take the square root. The hypotenuse, okay, the hypotenuse is 9,377.257, okay, minus the radius, 3,963. We get 414.3.